For topic 5, we're going to look at special cases. You might see books call this solving systems with unusual solutions. Same difference, okay? So, special cases, there are three situations that can arise when you're solving a system of linear equations, two variables, okay? You could have exactly one solution. That is everything we've looked at so far, okay? So that is where you have two lines that are very much independent of each other and they intersect at one point, which of course lines are only going to intersect at either one point or they're going to intersect everywhere. Okay. So this is everything so far. Okay. So all of our systems of equations so far had just the one solution. So one ordered pair solution that represented the point of intersection. Now, the first special case that you could see would be a situation where you have no solution. Now, keep in mind the solution to a system of equations is the ordered pair that satisfies both equations. So we have determined that that is the point of intersection. Well, if you have two lines that have no, or you have a system that is created with two lines that have no solution, those two lines would never intersect. They would be parallel lines. So anytime you have a situation where your system is created with two lines that are parallel, they're never going to intersect. There is no point that's going to satisfy both equations. We would say there's no solution, okay? So you have two lines that are completely independent of each other. They just happen to never intersect because they're parallel, okay? Now, special case number 2 is a situation where you're going to have infinitely many solutions, okay? We say these lines coincide. So what happens is you end up with two equations that actually graph the same line. So two equations that graph the same line. So again, we say these lines coincide. These intersect, well, let me rewrite that. We would say these two lines intersect everywhere. So these lines intersect at all points. So all ordered pairs that make up one line will also make up the other line. All right, so essentially these ordered pairs intersect everywhere, okay? Or these two lines intersect at all points from one line to the other, okay? So up to this point, all of the systems we have solved, there should be a D right here. So all of the systems we have solved have had a single solution, which is outlined in the first graph above. In the next example, we'll look at one situation where we have two lines that are parallel, and then we'll look at another situation where we have two lines that coincide, okay? So, example 5 says solve each system of equations. On the surface, you can't tell that anything weird is happening. You have to kind of dive in and solve the two equations or solve the system of equations or at least start the process, okay? Now, there are kids out here that are absolutely screaming and it's dark outside. When I was a kid, my parents would have tarred and feathered me if I acted like these little morons. Anyway, that is beside the point. So you can get some hints sometimes about the type of system you're going to have if you solve the two equations for y. Okay, so if you solve the two equations for y and you end up with the exact same equation, that would be a situation where your lines coincide. There are two equations that ultimately graph the same line. Okay, now if you were to solve for y and you had two equations that had the same slope but different y-intercepts, those would be parallel lines. So you could do some work to kind of get some hints about your equations, but in the time it takes you to do that, you could be halfway through with the solving process. So I say just dive in and start solving. There's going to be a trick, or not a trick, but there's going to be something that always happens that tells you you're going to have parallel lines or lines that coincide. Okay? So here's what we want to do. We want to start solving. It does not matter which method you use. You can use substitution or elimination, whichever one you prefer. Part A, I will tell you, was just custom made for substitution. Okay, we already have the first equation solved for x. So that tells me I want to take that value for x, which is 7 minus 5y, and I want to plug it into the second equation for x. So I want to take this right here and plug it in for x. Okay, so that would give me 7 minus 5y, and then the rest of the equation is plus 5y equals 12. Okay, well, now we have an equation in a single variable that we could certainly solve. And look at what happens. Notice right here we need to combine like terms on the left. Well, I have negative 5y plus 5y. So what would negative 5y plus 5y be? Well, that would just be 0, right? We would say these cancel. Now, just keep in mind, we get lazy as mathematicians and we're like, oh, it cancels. You have to understand that things either cancel because when we add them, they become 0, or when we divide them, they become 1. So in this case, I'm left with 7 plus 0 equals 12. Well, 7 plus 0 is 7. And unfortunately, 7 does not equal 12. This is a false statement. Okay? So when you're solving a system, my dog's about to go get mad at these kids for being so loud. So when you are solving a system, if the variables cancel, leaving a false statement, we have no solution, meaning the lines are parallel. So the way I would represent my final answer would just be to write out no solution. Okay? You don't want to do like some students when they're solving just linear equations in one variable, they'll do this like double backed R when we have the situation where X could be all real numbers. You can't really do that here because your solutions are not just real numbers, they're ordered pairs. So the best way to represent a solution here would just to say no solution. Okay? All right. So let's go back to Desmos. Let me take a picture of this because I don't have the actual worksheet in front of me. So let me take a picture so I don't forget it. All right, let's scoot over to Desmos so you can kind of see what this is going to look like when you type the equations in. Now, again, you could solve both of these equations for y, and if you ever solve two equations for y and you have the same slope and different y-intercepts, that indicates you have two lines that are parallel, okay? But for us, we're just going to type them in as is. So let's see, we had x equals 7 minus 5y. That's our first equation. Our second equation is x plus 5y equals 12. All right, and there you can see it. These two lines are never going to intersect. They have the same slope, they have different y-intercepts. If we were to zoom out, zoom out, zoom out, zoom out, we'll eventually zoom out so far that the two lines are going to look so close that it looks like they're the same line. They are definitely not. These two lines never, ever, ever intersect. Okay, so these lines are for sure parallel. Okay. Sorry for ranting about the kids next door, but they wear me thin. These kids act crazy. And it's like 4 different houses of kids, and they just scream all the time. So there's not a moment's peace if those children are awake. All right, part B. So we have another system, x plus 2y equals 2, and then 2x plus 4y equals 4. This one is a little easier to see because you could see if we multiply the top equation by 2, we get exactly the bottom equation, okay? But what we're going to do is we're just going to start the solving process, okay? And this equation right here is kind of set up to where elimination might be the better method for solving, okay? So what I'm going to do is it doesn't matter if I want to get rid of x or y. Let's say we want to get rid of x, okay? Well, in order to get rid of x's using the addition or the elimination method, I want to make sure these x's have opposite coefficients. Since the coefficient on the bottom equation already is 2 on x, so the bottom equation has a coefficient of 2 on x, we want to make sure the top equation has a coefficient of negative 2. So I'm going to multiply the top equation by negative 2, okay? And then that's going to give me a new system. It's not really a new system. It's the same system. It's just been jazzed up a little bit. So I'm going to multiply the top equation by negative 2. So that gives me negative 2x minus 4y equals negative 4. Bottom equation, we didn't mess with it at all. We're just going to rewrite it exactly as is. So I get 2x plus 4y equals 4. Add the two equations, and negative 2x plus 2x is 0. Negative 4y plus 4y is 0. And then negative 4 plus 4 is 0. So if I were to simplify, the left equals 0 and the right equals 0, which is true. My dog is mad at these kids right now. I hope y'all can't hear her, but she's going crazy. I need to hurry. Okay, so if the variables cancel, leaving a true statement, then we say the lines coincide, and we have infinitely many solutions. Now, what you don't want to say is that X is all real numbers. That is not how this one works. When you're in chapter 6 and you're solving linear equations in one variable and you get one of those situations where the variables cancel and you're left with a true statement, we would say that, hey, this shows that X is going to be all real numbers. The solutions to an ordered pair are not real numbers. They're ordered pairs. Okay, so we can't say X is all real numbers because all real numbers doesn't necessarily satisfy this system of equations. However, there are infinitely many ordered pair solutions, but they're very specific ordered pair solutions. Good Lord. There is a chihuahua out here barking at my dog. Anyway, so we can't just say it's any ordered pair. We have to be very specific about the ordered pairs that satisfy this system. It is the ordered pairs that make up either of these two lines. Okay, so this is a really weird way to write your answer. You start with squiggly brackets, and instead of stating just a variable, we want to say, hey, we're looking for ordered pairs. So write just a generic XY ordered pair and then do a vertical line. So this literally tells the reader we're looking for ordered pairs such that, and then just rewrite one of your equations. So we're looking for all of the ordered pairs that satisfy this equation. Okay, so every ordered pair that satisfies every ordered pair that satisfies this equation will also satisfy this equation up here. Okay, so it's kind of a really wacky way to write your answer, but keep in mind you cannot say X is all real numbers. If you say X is all real numbers, you'll get points taken off because X is not all real numbers. There are infinitely many ordered pair solutions, and they happen to be very specifically the ordered pairs that create these two lines. Okay, so let's go to Desmos and see what this looks like. So again, I'm going to try to hurry because my dog has lost her mind outside and I don't want her making my neighbors mad. All right, let's go to Desmos real quick. We're going to type in these two equations. All right, so the first equation we had was x plus 2y equals 2. So that's the first equation. All right, and then when we have the second equation, we had 2x plus 4y equals 4. And notice, it doesn't look like there's a second line, but there is. They're just two lines that are graphed one on top of the other. Okay, so every single ordered pair that you see here, so this ordered pair right here is an ordered pair that satisfies both equations. This ordered pair right here satisfies both equations. This one here satisfies both equations. There are infinitely many ordered pair solutions. They just happen to be the ordered pairs on this line or on these lines because technically it's two lines graphed on top of each other. And you can see we can keep zooming, zooming, zooming. These two lines are never going to separate from each other. They're the same equation. Okay? So that is graphing equation or systems of equations where you have the special cases. Remember, we have three situations. We have the situation where you have two independent lines that intersect once. You have the situation where you have two independent lines that never intersect. And then you can have a situation where you have lines that are not independent. They're the same line, and we say the lines coincide. Okay, so make sure you understand the different special cases. Okay, last up, we're going to look at some applications. So a couple of word problems with systems of equations.